Okay, so let's start implementing the quantum support vector machines in Qiskit. So let me share my screen. You can go to github.com MUF148 and go to this repository Quantum Machine Learning with Qiskit 2.x. And today I have uploaded three notebooks, QML 4A, 4B, and 4C. So 4A deals with the one toy dataset, and 4B and C they deal with leukemia dataset implemented with the two kernels. And let me go to the uh, code. Okay, so uh, this is the file QML4A, and in this I'm going to walk you through, how to compute a single entry of the kernel matrix, and then we will compute the all the kernel entries for the full matrix. For this purpose, I take a simple data set. It's actually the same data set that is in the, that's been used by the IBM learning platform for this support vector machine. So I'm keeping it because it is very easily classifiable. So it's a simple data. There are two data points. You see, there's this X vector with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features, and then there's label 1, and then there's another vector with 10 features and label -1. So these are just two data points. And what we are going to do is generate a simple Z feature map, and then use that to compute the kernel matrix. So we are using this Z feature map, and the number of dimension is same as the uh, feature dimension is the same as the number of data points in the training data. And you see that there are 10 qubits, and there are two unitaries that we are generating. So there is a unitary 1 with this feature map, and it's assigned parameter training data 0. And there is this unitary 2, which is assigned a training data point 1. And then we are just displaying. So this is the first unitary circuit. This is the second unitary circuit. For kernel, we know that the one unitary has to come as phi of x as it is, and the other is going to come as phi dagger. So for this purpose, you can use this function unitary overlap. So this unitary overlap automatically takes the dagger of the second circuit. You don't have to take dagger explicitly. You will take a dagger only if you want to generate this circuit yourself. In that case, you put the first part as it is and the second part as the inverted circuit. You can easily see that this is the forward circuit, and then this is the dagger part of the circuit. So anyway, so this is how the circuit for computing the kernel entry is generated, and the circuit depth is 9. And once you compute this, you set this circuit up, you can work it out on the quantum computer or on the uh, uh, on a simulator. So the code here shows how to do it on a quantum computer. So this just gives your parameters of the circuit, as we explained in the day one part of the lecture. And then you can summon the least busy backend. In this case, it's Torino. And to pass the circuit to this Torino, we can transpile it using this preset pass manager, and you can set the optimization level 3. This is usually helpful, because it optimizes your circuit for quicker implementation. And then you can check the transpile circuit as well. And to run it on to compute the entry, we can run it, let's say, for 10,000 times. So once we run it on the computer for 10,000 times by specifying the shorts and giving the overlap circuit, you can see that we can compute we can get the counts out of this. And once we have this counts, we can convert it. You can either get the integer counts by this get int count, or you can just get the counts with with this get counts method. And once we have this number of counts, we can plot it. For example, here I'm showing the counts, uh, the plots of the distribution of the counts, and you can see that all the possibilities are here. And if you want to compute the kernel entry, so for kernel entry, what you want to do is take find out how many times 0000 state appeared and divide it by the total number of shots. And this is how we are computing the kernel entry, as I was explaining in the lecture. So once we have this single kernel entry, we can repeat the method over a loop and compute the full kernel matrix. And for this purpose, we are transporting, we are, using a data set, and you can import this data set by clicking on this link, and you can download this CSV file on your computer. And there are 90, I'm going to divide it into 90 training data and 30 for the test data set. And from the file, we can get the X value and the labels by accessing this df variable. And similarly, uh, 30 data points have been put into the test set. Now, before we run the loop, let's create an empty kernel matrix. So there is a number of samples, 90 plus 30. And actually, if you just want to use the training, then the training samples are 90. And then there is a kernel matrix, which is actually a training matrix, because we only take the training data. And then there's a test matrix. This is a matrix for computing the inner product between test sample and all the training samples. All right. So once we have this, we can again create the circuit over here, just like this. So this time I'm not using the ZZ feature map. I'm using another feature map, which is customly built with this untangler plan. And you can see that by running this loop, and then having this loop first to compute this this CZ gates, we have generated this map. You can try other maps as well. So once we have this feature map, we can use it to generate the kernel matrix. And I'm going to be running the kernel matrix on simulator. So just initializing the test and train size and kernel and test matrix again. And once we have this, let's see how we can compute the kernel matrix. So you see that there is a loop over the training set once, and then another loop over the training set, because we have to uh, have one unitary for each of the data points, and then another unitary for each of the other data points. And you see that in addition to assigning these X features, I'm also assigning an additional parameter over here. And this is the parameter that I inserted in the circuit over here. You see this very small theta over in this RY gate. All the feature values are here, like this X0, X1, up to X12. But over here, there is this trainable theta, which I'm not actually training. It's just over there to show you that you can keep trainable parameters. Over here, it's just fixed at pi by 2. In the next file, I'll simply eliminate it, but I'm keeping it here to show you that you can treat this as a hyperparameter. So anyway, it's with unitary overlap, we are creating the circuit, and then again, we are running the sampler, which in this case is just an estimator, which is just a simulator. And once we find the counts, from the counts, we get the counts for the zero state and divide by number of shots to compute the kernel matrix entries. And we see that since we know the kernel matrix has to be symmetric, we don't need to compute all entries actually. If we know the entry for x1, x2, the entry for x2 and x1 is exactly the same because of the matrix being a symmetric matrix. And we don't even need to compute the entries when both the entries on the diagonal when both points are the same. We can just plug in one ourselves. All right, so once the training is done, we can do the same for a test matrix. So all we need to do is compute the inner product of everything in the test data set with everything in the training data set, and then everything else is exactly the same. All right, and once we compute the training metrics, you can easily visualize it using with this im show command. So this is the plot of the kernel matrix, and this is the plot of the test matrix. You see there are like 90 points in the kernel matrix, so the entries are here, and this diagonal is just all one. So this test matrix, there are like about 30 points in the test set, and their inner product is being computed with every point in the training set. All right, so once we have this kernel matrix, we can substitute this kernel matrix into this SVC class. So this SVC class is imported from sklearn. It's a state vector classifier, and you just give it a kernel as the kernel matrix and provide the training label that it should train to. So these are yi that we were talking about, and this kernel matrix is that k of x prime that we were talking about in the lecture. And it fits and it trains the model. And once it trains the model, we can compute the training accuracy by providing it the train label, and we can compute the test accuracy by providing it the test matrix. And you see, we are very lucky because it's a very simple data set, and the quantum state vector classification training and test accuracy is 100%. And just as a comparison, I trained it using the default linear kernel matrix for the classical SVC. And you see, if we do that, the basic accuracy training is 91, and the classical test accuracy is 67%. Okay, any questions? If not, let's go to the second file. Actually, let's go to the 4B. And this is almost similar, except that I will directly compute the full matrix. And I'm using this leukemia data set that we use for quantum variational circuit. And we are dividing it into test and training set. And I'm scaling the data to be between 0 to 2 pi. And once we have this data scaling, I'm splitting it into 80% training and 20% set. And then let's use the same feature map that we just used, okay? So this was the feature map that gave us 100% accuracy for the other data set. And if we use this kernel, this feature map, we can compute this, kernel matrix directly. And it's exactly the same, routine. And I'm just keeping this theta fixed. And for example, this time this theta is just fixed at 0. You can just change this theta if you want to find out accuracy as a function of theta. And actually in this model, this theta doesn't really impact too much. So once I have this test and training matrix, I used it in the training of this quantum state vector machine, and I got 70% training accuracy and 60% test accuracy. And just to compare it with the classical, so the classical is 68% and 67% for this data set. Okay, so let's see if we can do better. So for this purpose, I was experimenting with different feature maps, and then I realized that this ZZ feature map with 2 repetitions actually gives quite good results. So with these ZZ feature map, if you compute the kernel matrix and test matrix, you can get an accuracy of 100% on the training set and 66% on the test set. And actually, if we just make, let's say, repetition only 1, let's see what we get. Okay, so you do see that the choice of this kernel actually impacts the training and test accuracy very well. And what you have to do in this course to I uploaded an exercise where I'm asking you to come up with a feature transformation map that gives us a training and test accuracy of more than 85%. So it's easier to get a training accuracy higher than the test accuracy. So I invite you to do experiments with different feature maps and see if you can get the test accuracy above 85% for this data set using quantum support vector machines as well. So while this is running with the single repetition, let's see if there are any questions from you. It's gonna take a couple of minutes. Okay, so training kernel matrix is done. The test matrix is being worked out. And while this is, being done, let me request you to send me any feedback about this workshop to Gibran, where we can improve the things or which things were good that we should keep it the same way if I ever repeat it anywhere.
Sure. We can do a general feedback form as well overall.
Okay, that will be great, Gibran.
Yep.
All right, so with the single repetition, we got a training accuracy of 87 and test accuracy of 66. And you just saw that with 2 repetition, the training accuracy, went to 100%. So this shows that, more complex kernel matrices based on, more expensive feature transformations can give rise to a better classifier. So with this, let me see if there are any questions. If not, so thank you very much. And this concludes this quantum machine learning workshop as part of Quantum Barsat. And hopefully many of you will be here next week as well.